All right, let's go. Number 10. The incompleteness wound. Kurt Gödel was not trying to break mathematics. In 1930, he was a 24-year-old logician in Vienna working on David Hilbert's program, a decades-long project to prove that mathematics could be made complete and consistent once and for all. He was trying to help finish the foundation, not demolish it. Hilbert's program predicted something reassuring. Given a strong enough axiomatic system, every true mathematical statement should eventually be provable within that system. No gaps, no orphan truths, just proof, all the way down. Then Gödel found a sentence that could not be proven, yet was true. Not false, not undecidable garbage. True and unreachable. Gödel published his result in 1931 in Monatschäfte for Mathematik und Physik, titled On Formally Undecidable Propositions of Principia Mathematica and Related Systems. Using a technique now called Gödel numbering, he built a mathematical sentence that essentially said this statement cannot be proven within this system, and showed that any consistent system powerful enough to describe arithmetic would always contain such a sentence. Hilbert's team tried to patch it. Add more axioms, they said. Gödel had already accounted for that. Any expanded system just generates a new unprovable truth of its own. John von Neumann, who was in the audience when Gödel first presented the idea, immediately understood there was no fix. Von Neumann abandoned his own related project days later. This isn't a limitation of a particular exam question. It's baked into the structure of formal logic itself. Every rulebook powerful enough to describe numbers is, by necessity, incomplete, and it doesn't stay in the abstract. Any system you use to justify your own beliefs, including the reasoning inside your skull right now, either contains truths it can't prove about itself, or it's too weak to be useful at all. So which one is your mind? That single sentence in Vienna in 1931 has never stopped generating questions. Number 9. The Banach-Tarski duplication. Stefan Banach and Alfred Tarski were working in Poland in the early 1920s on a straightforward-sounding question in measure theory. Is it always possible to consistently assign a size to every subset of space? A tidying-up exercise in the foundations of geometry. Ordinary geometry says volume is conserved. Cut a solid ball into pieces, move those pieces around using only rotations and translations, reassemble them, you should still have the same total volume you started with. That's not a suggestion. That's supposed to be a law. In 1924, Banach and Tarski proved you could cut a solid ball into a finite number of pieces. Rotate and reposition those pieces with no stretching, no adding of material, and reassemble them into two solid balls, each identical in size to the original. They published the result in Fundamenta Mathematicae in 1924 under the title Sur la decomposition des ensembles de points en parties respectivement congruentes. The proof leaned on the axiom of choice, a principle most mathematicians already accepted as obviously true. Mathematicians tried to dismiss it as a trick of infinity, nothing physical. Fine, except the axiom producing it is the same axiom quietly underwriting huge parts of modern analysis. Reject the axiom to save your intuition about solid objects, and entire branches of mathematics collapse with it. Keep the axiom, and volume itself stops being a reliable concept for certain sets. There is no version of this where you get to keep everything you believed. The pieces required aren't cubes or shards. They're infinitely tangled, non-measurable clouds of points that cannot be built, drawn, or even fully described. Nobody has ever performed a Banach-Tarski split, and nobody ever will. But it proves that the concept of volume, something you have trusted with your body since childhood, is not guaranteed to behave the way you assume once infinity gets involved. If size itself can be that unstable, what else are you certain of, purely out of habit? Number 8. The Russell contradiction. In 1901, Bertrand Russell was reviewing the foundations Gottlob Frege had spent years building, an attempt to reduce all of arithmetic down to pure logic and set theory. Russell wasn't hunting for a flaw. He was trying to understand and extend Frege's system. Set theory at the time assumed you could define a set by almost any coherent property, and that sets could freely contain other sets, including themselves. It felt intuitive. Nobody saw a problem coming. Russell asked one question. Consider the set of all sets that do not contain themselves. Does that set contain itself? If it does, it violates its own defining rule. If it doesn't, then by definition it belongs inside itself. Both answers are contradictions. Russell communicated the paradox to Frege in a letter in June 1902, just as Frege's second volume of Grundgesetz der Arithmetik was going to print. Russell published the full argument in the Principles of Mathematics in 1903. Frege added a stunned postscript to his own book, admitting his life's work had a hole in its foundation. Ernst Zermelo tried to patch it with restricted set formation rules in 1908. Zermelo, Frankel's set theory, still the industry standard today, essentially exists because of this one contradiction, a permanent scar tissue wrapped around a wound that was never actually healed, only avoided. Frege never fully recovered his research program. He shifted directions and published relatively little of consequence afterward. This isn't a semantic trick about language. It's proof that unrestricted self-reference inside a logical system can generate contradiction from nothing but a single well-formed sentence. You define yourself, your identity, your beliefs, using self-referential categories every day. How many of them would survive Russell's question? Every foundation gets rebuilt after this one. None of them get to feel as solid again. Number 7. The unanswerable infinity. Georg Cantor wasn't looking for a paradox in the 1870s. He was trying to compare the sizes of infinite sets, a problem most mathematicians of his era considered borderline meaningless. He discovered that some infinities are provably larger than others. The real numbers are a bigger infinity than the integers. Naturally, the next question follows. Is there an infinity sitting in between the size of the integers and the size of the real numbers? Cantor assumed the answer was no. He called this assumption the Continuum Hypothesis, and he spent years trying and failing to prove it. In 1940, Kurt Gödel showed the Continuum Hypothesis could not be disproven using the standard axioms of set theory. In 1963, Paul Cohen, working at Stanford, showed it also could not be proven, publishing the result in the Proceedings of the National Academy of Sciences. Cohen invented an entirely new technique called forcing, specifically to pull this off. Put those two results together, and you get something almost nobody expects the first time they hear it. The Continuum Hypothesis is independent of standard mathematics, not unsolved, not pending better tools. Formally, permanently undecidable within Zermelo-Frankel set theory. Mathematicians proposed new axioms to force a resolution, large cardinal axioms, projective determinacy, dozens of candidate patches. None of them command anywhere close to universal agreement decades later. Cohen received the Fields Medal in 1966, the only Fields Medal ever awarded for a work in mathematical logic, for proving that a question could never be answered. This means the size of infinity itself, arguably the most basic property a set can have, is not fixed by the rules mathematics currently runs on. There is a hole in the number line's own architecture, one that no future genius will ever close, because closure isn't on the table. Somewhere between the integers and the real numbers sits a question with no answer anyone will ever reach. Not incorrect, just permanently open. Number 6. The random number that provably exists. Gregory Chaitin in the early 1970s was trying to formalize what randomness actually means for a string of digits, an attempt to put Kolmogorov's ideas about algorithmic complexity onto firmer footing. A tidying up project in computer science, nothing more. Ordinary intuition says any specific number, however strange, should in principle be calculable to as many digits as you want, given enough computing time. Chaitin constructed a number, now called Chaitin's Omega, that represents the probability a randomly chosen computer program will eventually halt rather than run forever. And he proved it is not just difficult to calculate. It is formally, provably impossible to compute beyond a small number of its own digits, no matter how much computing power or time you throw at it. Chaitin published the core results across several papers in the Journal of the AC in the mid-1970s, building directly on Alan Turing's 1936 halting problem. Omega is a specific, well-defined real number between 0 and 1. It exists. It has a value. And that value is, by mathematical necessity, incompressible. No formula shorter than the number itself can generate it. Researchers hoped clever new algorithms might eventually crack more of its digits. Chaitin's own Incompleteness theorem, a direct descendant of Gödel's, shows that any given formal system can only ever pin down a finite number of Omega's digits before running out of power completely. Add stronger axioms, and you gain a few more digits, then hit the wall again. Forever, this is a mathematical proof that true randomness is not just hard to find. It is guaranteed to exist, sitting inside a specific number permanently and mathematically sealed off from you. Somewhere in that number are digits no version of mathematics, run by any civilization, will ever legally reach. Number 5. The countable contradiction. Thorolf Skolem, working in Norway in the early 1920s, was examining a technical result about the Zermelo, Frankel axioms, checking what kinds of models satisfy them, a routine consistency check, not a search for paradox. Cantor's theorem guarantees that the real numbers form an uncountably infinite set, strictly larger than the countable infinity of the integers. That's settled mathematics, proven decades earlier and never seriously challenged. Skolem then showed something that looks flatly contradictory. If the axioms of set theory are consistent at all, they must have a model that is countable, a version of the mathematical universe, containing statements about uncountable sets, where every single object in that universe can be numbered one by one. Skolem presented the result in 1922 at the 5th Congress of Scandinavian Mathematicians in Helsinki, building on the earlier Löwenheim-Skolem theorem. He called it a paradox himself, in print, because even he found the outcome deeply strange. The resolution, such as it is, only makes things stranger. The set is uncountable from inside the model. There is no internal listing procedure that can enumerate its members, even though from outside the model, an observer with a wider view can count every element in it. Uncountability, it turns out, isn't an absolute property of a set. It's relative to which mathematical universe you're standing in. Skolem himself used this to argue that set theory could never fully pin down what infinite even means, a conclusion many mathematicians found more unsettling than the paradox itself. Which raises an uncomfortable question about every unlimited and infinite concept you've ever trusted, including the ones underneath the physics of your own universe. Unlimited relative to what vantage point, exactly? Nobody standing inside their own model gets to check from the outside. Number 4. The model that shouldn't exist. Leopold Löwenheim in 1915 was investigating a technical property of formal logic, whether certain statements have the same truth behavior across different size structures. A narrow, largely overlooked paper at the time. Common sense suggests a mathematical theory built to describe something enormous, uncountably infinite structures, for instance, should only apply to enormous, uncountable models. Small models shouldn't be able to fake being big. Löwenheim, and later Skolem extending the result in 1920, proved that if a first-order theory has any infinite model at all, it also has a countably infinite model. Even if the theory was explicitly constructed to describe uncountable infinities. Löwenheim published in Mathematische Annalen in 1915, Skolem's extension appeared in 1920. This means first-order logic, the primary language mathematics is written in, is structurally incapable of pinning down the size of infinite structures. Any theory rich enough to talk about huge infinities is automatically satisfied by a much smaller countable stand-in, hiding inside the exact same axioms with no internal way to tell the difference. Mathematicians tried moving to second-order logic to force theories to describe only the intended size of structure. Second-order logic fixes the sizing problem but breaks completeness. You lose the guarantee that every true statement is provable, trading one wound for another. There is no version of formal logic that gets both properties at once. If your entire framework for describing the real numbers or physical spacetime is written in first-order logic, and most of formal mathematics is, then a countable imposter model satisfies every single axiom you've ever used to describe it. The theory you trust to describe the size of your universe cannot, on its own, tell a giant structure apart from a small one wearing its clothes. Number 3. The truth proof can't reach. Gerhard Gentzen, in 1936, was trying to repair part of Hilbert's program after Gödel's blow, attempting to prove the consistency of basic arithmetic using tools slightly outside that arithmetic itself, a patch-up job, not a demolition. The assumption baked into centuries of mathematics is simple. If a statement is true, there exists somewhere a valid proof of it inside a sufficiently strong formal system. Truth and provability were treated as functionally the same thing. Gentzen proved the consistency of arithmetic, but only by using a principle called transfinite induction that arithmetic itself cannot justify internally, meaning the proof works, but only by stepping outside the very system being proven consistent. Gentzen published the result in Mathematische Annalen in 1936. Later, in 1977, Jeff Paris and Leo Harrington, working independently, found something sharper still, a genuinely mathematical statement, the Paris-Harrington theorem about finite combinatorics that is true, provably true using stronger tools, and yet formally unprovable within standard Peano arithmetic. Not an abstract logic puzzle. An ordinary-looking claim about numbers. Mathematicians hoped Gödel's original unprovable sentence was a strange, artificial, self-referential outlier, a rigged example unlikely to show up in real mathematics. Paris and Harrington closed that escape route. Natural, non-self-referential mathematical truths can be permanently unprovable too. That gap between what's true and what's provable isn't a rare edge case confined to logicians' basements. It's a structural feature sitting inside ordinary number theory, waiting, which means some of the beliefs you hold as obviously true, right now, about the world, may be correct, and permanently beyond your capacity to ever prove. You'll never know which ones. Number 2. The $1 million wall. Stephen Cook in 1971 was trying to classify how computationally expensive different logical problems are, organizing computer science's toughest problems into tidy categories, foundational housekeeping work at the University of Toronto. Computer scientists assumed, reasonably, that problems easy to check should also be easy to solve. If verifying an answer takes a blink, finding that answer shouldn't take forever. Cook proved that an entire massive class of problems, now called NP-complete, are all secretly the same problem in disguise. Solve any one of them efficiently, and you've solved all of them efficiently. Nobody has ever managed to solve even one. Cook published The Complexity of Theorem Proving Procedures at the 1971 Acom Symposium on Theory of Computing. Leonid Levin, working independently in the Soviet Union, arrived at essentially the same result around 1973. In 2000, the Clay Mathematics Institute named P versus NP one of its 7 Millennium Prize problems, attaching a $1 million reward that remains unclaimed. Thousands of attempted proofs have surfaced and collapsed. Every major approach tried so far, including the 2 most promising general strategies called relativization and natural proofs, has been mathematically shown to be incapable of resolving the question, ruling out entire categories of future attempts before they're even made. Nearly all of modern encryption, the systems protecting your bank account, your medical records, and every private message you've ever sent, rests on the unproven assumption that P does not equal NP. Nobody has verified that assumption. We have simply never found a counterexample. If someone proves P equals NP tomorrow, the digital locks protecting your entire life don't degrade. They fail all at once, everywhere, simultaneously. Nobody knows if that proof already exists, sitting unfinished on somebody's desk. Number 1. The sentence that breaks itself. G. Berry, a junior librarian at Oxford's Bodleian Library in the early 1900s, wasn't publishing groundbreaking mathematics. He noticed something odd about language while cataloging, and mentioned it in correspondence to Bertrand Russell, who recognized its weight immediately. Ordinary language assumes you can describe any number you like, given enough words, and that some very large numbers simply require more words to pin down than others. Consider the phrase, the smallest positive integer not describable in fewer than 20 words. That phrase itself contains exactly 13 words. It just described, in 13 words, a number it claims cannot be described in fewer than 20. Russell formalized and published the paradox in 1906, in Les Paradoxes de la Logique, in the Revue de Métaphysique et de Morale, crediting Berry by name for the original observation. Kurt Gödel later cited Berry's paradox directly as part of the inspiration behind his own 1931 incompleteness proof. This quiet Oxford library note sits in the intellectual bloodline of the most important logic result of the 20th century. Mathematicians initially dismissed it as sloppy natural language, not real mathematics. Describable in words isn't rigorously defined, they argued. But Chaitin later built a fully formalized, rigorous version of the same contradiction directly into algorithmic information theory, using precise programming language length instead of English words. The rigorous version breaks exactly the same way the sloppy one does. This means self-reference doesn't need exotic set theory or advanced logic to generate a genuine contradiction. It was hiding the entire time inside plain sentences in a library, waiting for someone bored enough to phrase a description carefully. You use self-referential language about yourself constantly. Sentences about your own thoughts, your own honesty, your own mind. How many of them are quietly doing exactly what Berry's sentence does? Nobody has ever found the 21st word that fixes it. 10 glitches. 10 different corners of mathematics, from library shelves to the size of infinity itself. None of them sit at the edges of some obscure specialty nobody uses. Every one of them sits inside the machinery holding up arithmetic, logic, computer science, and the proofs underneath modern physics. The universe isn't confused. Mathematics, the one tool we built specifically to never be wrong, turns out to contain permanent, provable holes in its own foundation. Holes that aren't going away, aren't getting patched, and aren't anyone's fault. We just proved, mathematically, that certainty was never fully available to begin with. If you want to see more videos like this, click the video on screen now.